certain chemicals favor different methods of detection. And I mentioned three of them. There's optical detection, acoustic detection, and then chemical reactive detection. So to talk about optical for a moment, certain chemicals in the air, they will, for more or less terms, refract with varying wavelengths of light. And so if you can find that specific wavelength and you get a signal back from that refraction, then it's indicative of what chemical that might be, right? So alcohols might refract in a very certain way. Organic compounds in general might refract in a very specific way or a very specific wavelength. And so this spectroscopy or these infrared techniques are one way to detect certain chemicals. Now, some favor optical detection, others favor chemical detection. So as an example, for chemical detection, if you think of a battery, right, there's an there's an anode and a cathode, and there's an electrolyte. And the electrolyte is charged. Now, it's charged. The electrolyte is designed in a certain way such that if it hits a certain charge, then it will react with a specific group of compounds. For example, alcohols or aldehydes or something like that. So it basically, as the chemicals interface with the electrolyte, they send a charge back depending on how the electrons interface with the electrolyte. And so it gives you an indication of what chemicals are around you. And then similarly with acoustic sensors, the vibration of chemicals at a quantum level, you can detect the frequencies of those vibrations, and those different frequencies determine what chemical you're looking at.
That's cool.
Yeah, so it's a matter of like the mediums are all there, the ways of detection are all there. The problem is really, how do we compress these lab instruments that have been used to illustrate these techniques down to such a small form factor that they can be used on, handheld devices or robots?
Yeah. So how do you go about that? Because that does sound like the big problem. So I guess you're saying that these are, it's well established in a sense to use sight, acoustics, and chemical reactions to find things that are, to basically infer about what is in the air. And from that, you can infer something like scent. And, but so these are fridge-sized things or large devices. How are you going about and combining and minimizing these? Like, I imagine that's probably the bulk, or that's a huge challenge that you've been working on with the previous company and now current company.
Yeah, a lot of my PhD research went into it as well, to try to understand. You really have to understand the current state of the art and how these systems work. And there have been a lot of great engineers that have worked on these things, and so they've optimized them really well. And so it's a matter of really, can we optimize further? And if we can't, what constraints can we relax in order to get a smaller size, weight, and power factor? So like, for example, there's an instrument called the GCMS, which stands for Gas Chromatography Mass Spectrometry Machine. And it's about the size of a fridge. And it takes hours to run an air sample. Now, it's very accurate, and it gives you very detailed results. But if you can imagine something like a dog, which has like 100 hertz refresh capability in its olfactory senses, that's not very competitive to something that takes hours to run, right? So maybe if we can relax the accuracy and the number of compounds we're looking at, we can get a smaller, size, weight, and power factor.
Okay. And so you did that for those 3 domains of sensing. How do you make it so that there is, because I imagine, and maybe it depends on the use case that you want. I imagine it's quite specific on the use case. Tell me about that a little bit.
Yeah. So if you want just like passive monitoring, like for example, with like quality control of food or drink or produce or floral, you don't need 100 hertz refresh capability, because the problem doesn't define that type of a solution. So you can get away with a longer refresh rate, a longer detection time, and have more accurate responses. Now, something like olfactory navigation, like how a moth or how a dog actually navigates the world, that's where a really fast refresh rate comes in handy, because you really need to be able to update your world state much more quickly and respond to actuators, right? If I need to drive left because the scent plume is moving left, I don't want to wait an hour to do that because the scent plume changes several times a second. So you've got to be able to react in a very, very quick way. So those types of things are taken into consideration for the products that we build. So we have two products. One that is a fast responding, very low size, weight, and power product that really is tuned for olfactory navigation, and one that's a little larger, that about the size of a coffee maker, that allows you to profile the air around you or an air sample and get, at the expense of a longer detection time, get much more higher accuracy and a much larger array of chemical compounds that can be analyzed.
Okay. Very cool. I would love to hear about the use cases you're targeting for both of these, the small one and then the large one. Did you have the small one nearby? You held up something earlier. I don't know if that was it.
I do, yes. So we've got one of them here. This is a smaller one, and it's really built to, and it'll shrink in size as the company grows, but we've built it to be able to be used by robots, right? So that they can integrate this with a very low size, weight, power factor, have an API that they can talk to very easily, and really navigate the world. I mean, if you're familiar with what's going on with like Figure or Tesla Robots or Apptronic or Fourier or any of these really big robotics companies that have gotten billions of dollars in funding, they all have vision, they'll have audio, they'll have speech capabilities. They have haptic capabilities and tactical capabilities since they can walk around, but they're missing the sense of smell. And when you mention that to people, they're like, okay, well, why do I need that, right? Well, if you think about the applications, you really expand the capabilities that robot can do by giving it the sense of olfaction or smell. So being able to detect when there are high traces of carbon dioxide in the home, or being able to quality control food and manipulate produce around to fit in a grocery store, right? Like those are things that a robot currently won't be able to do unless it's given a sense of smell.